Hi, welcome back to the breadboard. Today we're going to have a look at a power supply, DIN rail mount, 24 volt and 10 amp power supply, just checking off the top. This one is from Phoenix Contact and it's a QUINT4 power supply. It's one of their new range that has a little bit of smarts built in, and one of the key features that differentiates this from a number of other power supplies is it also has near field communication, so you can use your cell phone to actually configure the power supply, which is kind of cool. It has controls on the front panel as well. We'll have a look at that in a moment, of the power supply that allows you to do things like adjust its voltage between 24 volts and about 29 volts, and also tweak a few other parameters. For instance, what happens when you overload it? Does it shut down? Does it wait a little while to see if it's just a transient, etc., etc.? And it has some signaling outputs as well that allow you to indicate to some other remote or near device what kind of power is being consumed, is the output voltage okay, and a few other things. And we'll have a look at all these configuration items as we go. For now, let's go have a close look. I've got a little bit of a test setup on the bench here so that we can look at it. So this is my setup. The QUINT4 that I have is the 24 volt 10 amp version, so 240 watt. Have mains input here via this cable, goes to a quick test box which is available from RS Components. We have a voltmeter here, well, multimeter. Initially I'm going to be measuring the output on output 2. I've just got to move this because I was doing something else before with it. It's one of the signaling outputs. The QUINT4 has a number of different outputs. One is a remote signal into the power supply that allows you to shut it down, or at least the output stage of it, remotely if you want to, say for instance from a PLC or some other control aspect if you desired it. Leaving the contacts open between REM and ground causes the power supply to work normally. The top two pins are marked 13 and 14. These are completely isolated contacts that can close based on different conditions that you can program. You can't program them from the front panel here, but you can program them using NFC communications, either from a smartphone or from a PC with an USB to NFC adapter that's been built to talk with this. You also have out 1 and out 2. Out 1 is a digital output that can be programmed for signaling different states. Out 2 is also digital, but can also actually provide you an analog output that can represent either the voltage that's set, the current that's being consumed, or the power that the power supply is delivering to a load. So what I have here, I've connected the output of the power supply to my manual constant current load, so I can set a current on here just by adjusting this potentiometer, so we can load the power supply up and we can see what's happening with the current here. Now it outputs a current on 2 when you're using analog as a 4 to 20 milliamp signal, which is an industry standard. And what I'm going to do is I'm going to hook this into my multimeter. So I'm just going to switch this to current range, to milliamps, and we will be able to see what this represents. Now the power for this is not 240 watts and it's going to be 4 to 20 milliamps, so we'll be able to figure that out. Now normally if you were feeding this into a PLC, of course, it would convert that directly to a power. If you were using the bigger unit, you can get one of these power supplies up to I think about 750 watts. Then obviously the scale of 4 to 20 milliamps would be different for that power supply. We'll look at the data sheets in a moment. I've never had this powered up and I haven't adjusted any of the settings, so we should get a nominal 24 volts out and probably set to 10 amps as the current limit. Now one of the other things that you can do with the Quint power is you can also set the way that it trips. In the case of a short circuit, you can set the current threshold and things like that. So unlike the Meanwells and other power supplies that we were looking at in the previous video, this specific one you can actually change quite a few of the operational parameters of the power supply. Anyway, let's power it up and just see right off the bat what it's going to do. Now my DC load is not connected right now to a power source, so it's not going to start up. It's got a fan that automatically starts as soon as I power it up, and it gets a bit noisy, so I'm going to leave it off just for the moment. Okay, so let's power the power supply up. So we get the DC OK light immediately comes on here. Just in case you didn't see it before, there's the front panel. On the multimeter though, we can see we have 24.1 volts on the multimeter. Now I haven't set any DC load yet, so let me just plug that in and we'll set a load of about 1 amp and see what happens. Like I said, it's going to make a little bit of a noise, so excuse that. Right now we've got 600 milliamps. Let's just take it right off. So you can see the volts here is 24.1. It's just a little bit high, but there's no load. We'll take it up to 1 amp, and that's just 1.01 amps, and the volts has dropped just a tiny amount. So one of the front panel features on here is the ability to adjust the volts up to 30 volts from 24. So right now we're at 24. I haven't done anything with this yet, so let's just push this up button and we should be able to increase the volts. As you can see there, it's going up. 25, 26, should max out at 27. My DC load, of course, is keeping it at a constant 1 amp. Sorry, should max out at 29. So 29.5 is where it's maxed out, and according to the front panel, it is 29.5 is the maximum. So let's just take this back down to its nominal 24 volts. Now, why would you want to adjust the power supply output voltage up to 29.5 volts or anything in between? The reason for that is your load. If you have a little bit of a run to your load and you're losing volts because of the drop in the cables, you can actually up the volts on the power supply to compensate for those cable drops. And that's very, very useful to make sure you get more precise voltages on the remote end of a load without having to actually have a power supply that has remote sensing. You're just basically compensating for the cable runs. Just trying to get this back to a nominal 24 volts. So you can see pressing up and down buttons all the time like this is a bit of a pain. There we go, 24.001. So based on a 1 amp load with a short piece of wire, I'm going to be dropping a little bit of volts across here. We've got 24 volts exactly with 1 amp. Now I'm going to connect my meter now to the output of the analog. I don't know whether it's set up yet for analog output, but we'll just hook it up and see. Right now I'll put it on volt mode to start with. So it's outputting 23 volts on there, so it may well already be set up for some kind of current output. So let's try and switch it to milliamps. We'll put it in the amp socket first. So it's outputting 24 into that load, 24 milliamps. So that looks like it's probably not set for a current output at the moment. It's probably just set for a logic output. So the next thing to do is to go in and look at what settings we can do. But first, let me just increase my load to the maximum I can on my DC load just for the moment. I think I can only go up to about 5 amps, not 10 amps. Yeah, 5 amps. So that's not making any difference. Sorry, I just realized you can't see the front panel of this. So with the flicker, it's a multiplex display, but we'll set it back to 1 amp just for now. So 4 to 20 milliamps representing 10 amps, then, or roughly 10 amps, then if we change this to be current output on output 2, we should be able to get, that's 10% of the current, so therefore 2 milliamps. So that will be 6 milliamps what we should have once we have this set. Now, I don't think there's anything else here that we can set at the moment without having a phone near it. So let's just get my phone set up with the application. You just simply download it from the Play Store, and I'll show you what we can do with the programmability. So this is the Quint power application on an Android phone. So I've just started it up. Shows you the different power supplies, and you've got the option here of reading via NFC, starting a new configuration, or opening a configuration. So what I'm going to do is I'm going to tell it to read via NFC, and then I'm going to sit it on top of the power supply so that we can try and do a read here. I don't know if you heard that beep, but it just beeped at me. I'm going to put this back here and zoom in so you can see what it read. Okay, so it's identified the device as a QUINT4 24 volt 10 amp. Output voltage is currently set to 24.1 volts. Output characteristics is static boost, dynamic boost, selective fuse, braking. We'll look at those when we go into the data in a moment. Output 1 is set to go high if the output volts, which is U, goes above 90%. Output 2 high if the power goes over output 2 is high if power is less than 100%, and output is closed if UOut is greater than 90%. Control input, power supply on if input is open, and our control input, which is the remote lines on here. So if the remote, which is here, is shorted to ground, it will turn the power supply output off. If it's open, it will leave the power supply operating normally. So what we're going to do is we're going to change the configuration for the output characteristics. Alright, so now signaling, we're going to change the signaling here. Output 2 is the one we want for analog, so I'm going to change this to be able to use as analog output. So you just press the button, select analog output, and you can select whether it's output voltage, output current, or output power. So let's just set it to current to start with. We'll set start value for 4 milliamps is 0 amps, and end value is 10 amps. You can change that. So in the, you could change that to indicate 0 to 5 amps if you want, and just have some spare capacity depending on what you're nominally going to be doing. So I'm just going to leave it set for 10 right now. We'll go back now that we've done that, and now we want to write that to the power supply. So I've just hit NFC, take it and just put it over the power supply, and it very quickly just writes it to the power supply, and that's done. So now our output should be a 4 to 20 milliamp output representing a 0 to 10 amp load. Now I don't know if you have to power this off and back on again, but I noticed that we're still reading 24.9 milliamps on our output. So let me just cycle the power. I don't think it should actually need that, but who knows. I guess it does. When you change the configuration, it looks like you need to cycle it. So now we're reading 3.9 milliamps on our display on the multimeter. I'm just moving this closer so that you can see. And what I'm going to do is with my DC load here, I'm going to turn it back on, so it's going to get noisy again. Now, so this is representing a 4 to 20 milliamps, so 10% of that would be 6. So I'm going to set an amp, which is what this is set for. We should get a reading of about 6 milliamps there. And there you go, it's 5.5. So if I take this to 5 amps, it should be halfway through the range of 4 to 20 milliamps. So that's 16, that's 8 plus 4 would be 9, 10, 12 milliamps if I set this to a full 5 amps. So I'm just going up on here to read 5 amps, and we're just a tad short on 5 amps. But you can see here we've got just a tad short of the 12 milliamps. So the power supply is indicating that the current coming out is indeed half of the scale, because 20 milliamps minus the 4, which represents 0, is 16. That leaves you 8 for 50%, plus the 4 base gives you a reading of 12. So if I take this down to back down to 1 amp, that will be 1.6 plus the 4, which is 5.6 milliamps. I think I said it wrong before. let's just take this back down to 1 amp. And that should be about 5.6. So it's about 5.5 there. Now what I'm going to do is I'm going to reconfigure it to on here. So instead of having output current, I'm going to change this to say output power. Alright, so it's going to be 4 milliamps for 0 watts and 20 milliamps for 240 watts. Now because we can only go to halfway, that means it's going to be 120 watts. So we should get 12 milliamps showing on the scale again, but this time that will be representing the 120 watts. So again, I've set this to be analog output, output power. Let's go back to signaling, and we'll rewrite this to the power supply again, the same way as we did before. And that's done. So now we need to recycle the power supply again. I will verify if that is truly what it's supposed to be done. Now what we have here now is the multimeter is indicating the power that's being consumed. Now I guess the current and because the voltage is fixed, the current is going to be the same as what we had with the voltage scale. Alright, so I've maxed up to just below 5 amps, which is all I can get on my pot, and we're just below the 12 milliamps here, so it's indicating the power. Now the way to, I guess, get around this is to increase the voltage out to change what the power reading would be, because if we were just indicating current, it would make no difference because it's set to 5 amps. But let me just bring this down, and I'm going to increase the voltage now to 29.5 on here. So using the up voltage, I'm going to take it right up to the 29.5. So that's going to change the power scale, because 1 amp at 29.5 is going to be 29.5 watts. So it will be a little bit different. So there's the voltage right now. Just going to increase that all the way. If you're interested in the build of this DC load, constant current load, you can check out one of my videos. I'll put a link to it when I post this, because I have a whole project that I did actually creating this. It's nothing more than an op amp, a power MOSFET, second-hand heatsink from a CPU, a 3D printed front panel, and a voltage reference inside here. So it's quite a simple project, and I think that most people probably, you would find it handy if you're doing power supply work and things like that. Okay, so we've got no current right now. If I take this back up to 5 amps, all right, before we had 12.6 here. If I get a calculator, so we've got 30 volts now, well, 29.3 volts. So if I just pull up a calculator, wherever it's gone. So 29.3 times 4.94 is 144 watts, 144.7 watts. So if we take that as 240 watts as being peak, that's about 60% of the scale. So 16 milliamps times 0.6 plus 4 gives us 13.6 milliamps is roughly what we should be reading on the output, and we've got 13.9. So I'm a little bit out from my calculations, but I was just rounding off numbers. And I haven't tested the calibration of this recently, so it could be a little bit off, but probably not that much. Anyway, so now you can see that the current output here, 13.9 milliamps, is basically representing, well, 13.6 I have here, but that's within a couple of percent accuracy. It now shows us the power output of the power supply, and it has now been increased to 13.9 watts. Shows the power So there we have that. I've adjusted the voltage. Now you've seen that the power output has adjusted itself accordingly. So yeah, it's very, very useful. Now let's go look at the specifications and what other settings you can actually do with the power meter. So I'm going to go to my PC and capture the screen from my phone while we do that, so that we can actually have a clearer look at all the different settings that are available to us.